Go away! How can a small bee make so much sound?
Believe it or not, that noise comes from the bee flapping its wings fast, really fast. Actually, you'll be surprised to know all kinds of sounds are produced and propagated in the same way. This includes the sound that you hear on plucking at a rubber band, the tinny noise our little sister makes by banging a spoon against the vessels, even the sound of music played by your favorite guitarist.
Really? That's interesting. Tell me more.
In this lesson, you will learn about production and propagation of sound and the characteristics of a sound wave. At the end of this lesson, you will be able to define sound, explain how sound is produced, explain how sound propagates from the source to the listener, demonstrate that sound needs a medium to travel, compare longitudinal and transverse waves, identify the main characteristics of a sound wave, and compare the speed of sound in different media. Let's start with what sound is. Sound is a form of energy that produces a sensation of hearing in our ears.
You mean like heat?
Yes, of course. Here's an interesting experiment that proves it. To start, we take a tin can and remove the base and the lid of the can to create a cylinder open on both sides. Then we stretch a balloon around an open end of the cylinder and secure it with the rubber band so that a stretched membrane is formed. We then take a small mirror and stick it to the stretched membrane made out of the balloon on the outer side of the cylinder. Using a laser torch, we focus a light ray on the mirror such that it reflects on a wall as a spot. The final step is to shout in the open end of the cylinder.
This is an experiment.
Did you see how the reflected light spot moved on the wall?
Oh, yes.
If you shout again, it will move again.
This is an experiment.
As we shout, the voice moves because the vibrations are conveyed through the air to the stretched membrane. The stretched membrane gets tuned to the vibrations of the sound. As the membrane vibrates, the mirror on it also flutters. Hence we see the dancing spot. Now let's take a look at two situations where different types of sound are produced. What was common in both the cases where sound was produced? There was a to and fro motion of the parts of the bodies when they produced sound. This to and fro movement of an object is called vibration. Sound is produced due to vibration of objects. In the case of the guitar, it is the vibration of the strings that produced the sound. The buzzing sound is produced by the rapid vibration of the wings of the bee.
Really? It's a little difficult to believe.
Well, let's verify whether it is true through an experiment that should help convince you. Let's take a bell and ring it. Do you hear that sound? This ringing sound is due to the vibration of the bell's gong. Now, suspend a table tennis ball with a string to a stand. And then gently bring the ball in contact with the ringing bell. You will be able to see the ball flicker away from the bell and start swinging. This is because the bell is vibrating. This confirms that the sound of the bell was being produced due to vibrations. What is the difference between the sound emitted by a lion's roar and the sound produced by the rustling of leaves? A lion's roar is a high-intensity sound, while rustling of leaves is a low-intensity sound. Intensity of sound is the amount of sound energy incident per unit time per unit area. The sound intensity is normally measured in watt per square meter. To reach your ear, sound needs to propagate from the source to you through a medium. A medium is the matter through which the sound is transmitted. A medium can be liquid, solid, or gas.
So how does sound travel? Do the particles in the medium travel from the source to the listener?
No, not really. To understand the process of the propagation of sound, let's analyze what happens when we cause a vibration to produce sound. Now, let's see. What happens when we stretch a rubber band and plug it in the middle? The air particles of the medium, which are in contact with the vibrating rubber band, that is, the source of sound, are first displaced from their state of rest. These displaced air particles displace their neighboring particles and then come back to rest in their original positions. Thus, now another set of particles of air between the vibrating rubber band and the listener are in a state of vibration. These particles vibrate in a direction parallel to the line joining the rubber band and the listener. They in turn displace neighboring particles before returning to a state of rest. This process continues until the sound reaches the listener. As you can see, particles of the medium do not move from the source to the listener, but it is the disturbance in the particles that is carried forward to the listener. This kind of a disturbance is called a wave. In other words, a wave is a disturbance that moves through a medium when the particles of the medium set neighboring particles into vibration. Therefore, we visualize sound in the form of waves. Air is the most common medium through which sound propagates. To study the sound waveform in more detail, let's use a tuning fork. Vibrating a tuning fork produces a small audible sound. Vibration involves to and fro motion of the prongs of the fork about a fixed point. This fixed point is also referred to as the mean position. The vibrating prongs of the tuning fork push and compress the particles in front when moving towards the outer direction, creating a region of high pressure. In this region of high pressure, the density of air is higher than the normal. This region of high pressure is called compression. When the prong moves backwards, it creates a region of low pressure, called rarefaction. In this region, the density of air is lower than the normal. Thus, as the tuning fork vibrates, the to and fro motion of the prongs of the fork create a series of compressions and rarefactions in the air between the fork and the listener. These compressions and rarefactions comprise a sound wave that propagates through the medium. As sound waves travel as disturbances propagated through air by a mechanism of particle-to-particle interaction. They are termed as mechanical waves. Mechanical waves require a material medium for their propagation. A mechanical wave can be a transverse wave or a longitudinal wave. Sound waves in air are longitudinal waves. To understand what that implies, we need to first understand the two categories of waves. In transverse waves, the particles of the medium vibrate up and down about their mean position, which is in the direction perpendicular to the direction of wave propagation. When we fix one end of a string and vibrate the other end in a direction perpendicular to the length of the string, the wave pattern that is seen is that of a transverse wave. When a pebble is thrown onto the surface of still water, it creates small ripples. These ripples propagate through the expanse of the water as transverse waves. In fact, try and observe closely tiny particles and dried leaves on the surface when ripples are formed. These particles do not go with the wave, but just move up and down at their positions about a mean position. This figure depicts the propagation of a transverse wave. You will learn more about transverse waves in higher classes. In longitudinal waves, the direction of vibration of the particles in the medium is parallel to the direction of propagation of the wave. The wave pattern set in a slinky is an example of a longitudinal wave. Let's recall the tuning fork experiment. In sound waves produced by a tuning fork, particles of the medium vibrate in a direction parallel to the direction of wave propagation. This produces compressions and rarefactions in the wave, similar to that in the pattern showed by a slinky. Thus, we can see that sound waves in air are longitudinal waves. A complete sound wave can be considered as the repetition of the pattern of a single wave. That is, it comprises a number of compressions and rarefactions in succession. The length of a single wave is called wavelength. In other words, wavelength is the distance between two consecutive compressions or two consecutive rarefactions. It is denoted by the Greek letter lambda. Since a compression and a rarefaction follow each other in succession, sound propagation is a periodic phenomenon. The interval between the generation of two successive compressions or two successive rarefactions is constant and is referred to as the time period of the wave. Time period is denoted by T and is measured in seconds. For example, the time taken by a pendulum to complete one to and fro cycle is known as its time period. All of us have heard a clock tick. It ticks once every second and maintains the time period. The ticking of a clock once every second is the frequency of the clock. Frequency of sound is the number of waves produced in unit time. It is denoted by the letter N and is measured in hertz. Since the clock ticks once per second, its frequency is 1 hertz. Let's see how frequency relates to time period. The relationship between frequency and time period can be expressed as N is equal to 1 divided by T, where T is the time period Thus, if the time period of a wave is 1/10 of a second, then we get 10 waves in 1 second. The frequency of this wave is 10 Hz.
Ouch!
Yes, that hurt, didn't it? But listen to the cooing of this pigeon. Not so bad, was it? Why do you think the effect of both the sounds on our ears is so different?
Well, because our ears are not used to loud noises.
That's true too. The technical explanation, though, is related to a concept called pitch of sound. The pitch is the interpretation of frequency of a sound by the brain. Commonly, pitch is taken as the frequency of sound. A scream is a high-pitched sound, since the frequency of a scream is high. Similarly, the cooing of a pigeon is a low-pitched sound. The shorter the wavelength, the higher the frequency, and the higher the pitch of the sound. Simply put, short waves sound high. Long waves sound low. Let's listen to some music. Can you tell whether it is a single instrument or two instruments playing?
Yes, it is definitely two instruments. One sounds like a violin and the other could be a sitar.
You could identify the difference in instruments because of the type of sound you heard, right?
Yes.
Sound emitted by every instrument has a unique characteristic that distinguishes it from other sounds with the same pitch or loudness. This characteristic is the quality or the timbre of the sound. If you now listen to each of the instruments playing the same tune separately, here you can make out the difference in quality of both the sounds. Sometimes when you switch on your computer, you hear a long beep indicating a boot-up error. Listening carefully, you make out that this beep is a uniform sound. This beep sound has a single frequency. Thus, the sound wave shows uniformity. This is an example of a tone. A tone is a sound wave of single frequency. The man on the left seems to be listening to some good music. Proper mixture of frequencies results in a pleasant sound or note, which we term as music or musical note. Thus, a note is a sound produced due to a blend of several frequencies. If a note is not pleasant to hear, it's simply called noise. Now, listen to these sounds. Can you hear me? Can you hear me? What was the difference?
One sound was loud and the other was very soft. What makes these sounds different?
It is a characteristic called amplitude. The loudness of a sound depends on its amplitude. Amplitude of a sound wave is the maximum displacement of the vibrating particles from their mean position. It is represented by the letter A and depends on the force with which an object is vibrated. Greater the amplitude, louder the sound heard, and lesser the amplitude, the lower the audibility of the sound. Listen to these two sounds produced by the same drum. The second sound was louder than the first. This is because the amplitude of the sound produced the second time was higher. A loud sound can travel across a larger distance because it is associated with high energy.
What about the speed of sound though? How fast can it travel?
Comparatively speaking, the speed of sound is less than that of light. If you notice, on stormy days, we see the lightning first and then hear the thunder. That's because light travels faster than sound, and so lightning reaches us first. Speed is the ratio of unit distance to unit time. For a sound wave, the unit distance is its wavelength, lambda. And the unit time is the time period t. Therefore, the speed of a sound wave is the ratio of its wavelength to its time period. It is denoted by the alphabet V. You know that the reciprocal of a time period of a sound wave is equal to its frequency. Therefore, the speed of a sound wave is the product of its frequency n and wavelength lambda.
What about the speed of sound in a medium other than air?
Well, that differs from medium to medium. The speed of sound depends on the properties of the medium through which it propagates. The important properties that affect the speed of sound are the temperature and the density of the medium. If the temperature of a gas increases, its density decreases, resulting in an increase in the speed of sound and vice versa. The speed of sound in various media at specific temperatures is given in the table. From this table, you can see that sound waves propagate faster in solids than in liquids and gases.
And what happens when an object is moving faster than sound can move in that medium?
Very good question. Have you ever heard of sonic booms? When an object is traveling at a speed greater than the speed of sound in air, it is said to be at a supersonic speed. For example, a bullet fired from a gun travels at a supersonic speed. Some jet aircrafts, at times, travel at supersonic speeds. When an object, like a jet aircraft, travels at supersonic speed, it produces shock waves in the surrounding air. These waves carry enormous energy. This energy is propagated in the form of a sharp and loud sound called the sonic boom.
But then, what happens when there is no air or no other medium? What happens to a sound produced in such a situation?
Sound cannot travel in the absence of a medium. We know that the sun is a huge ball of fire. The reactions of gases in the sun result in explosions that produce light as well as sound. Why do you think we are able to see the sun's light, but not hear the sounds of these explosions? Because sound needs a medium to travel. We just said that sound needs a medium to travel. Let's verify this through an experiment. We take an electric bell and fit it in an airtight glass bell jar. The bell jar is connected to a vacuum pump from one end and a power supply with an on or off switch at the other end. On pressing the switch, you will be able to hear the bell ringing. Now suck out all the air from the bell jar using a vacuum pump. You will notice that as the air is being sucked out, the sound of the bell starts getting feebler. In fact, the sound of the bell is not audible at all once all the air in the bell jar is sucked out. That's because absence of air has created a vacuum inside the jar, meaning there is no medium in the jar now. This confirms that sound needs a medium to propagate. This brings us to the end of this lesson on production and propagation of sound. In this lesson, you learned how sound is produced and propagated. You also learned about longitudinal waves and transverse waves in relation to sound waves. Finally, you learned about some important characteristics of sound waves. The section on solved problems provides you an opportunity to review some model problems based on these concepts. Can you calibrate a stopwatch to directly show the depth at which the water is present? You can find clues to solve such a problem in Solved Problem 3. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.